Good morning, friends. Today we will discuss the reactions of alkyl halides or haloalkanes. Alkyl halides or haloalkanes are highly reactive in nature due to the presence of polar carbon-halogen bonds. Innumerable halogenated organic compounds are manufactured for commercial use. This includes synthetic plastic polymer like PVC, insecticides like DDT, linden, insulating fluids like PCB, that is polychlorinated biphenyl, and chlorofluorocarbons like freons. Do you know what is halothane? Halothane is an inhalation anesthetic with formula CF3CHBrCl. This inhalation anesthetic halothane derives its biological activity from polar carbon-halogen bond. So today we will discuss how this polar carbon-halogen bond present in alkyl halide governs its reactivity and converts the alkyl halide into different functional group. So this alkyl halide or haloalkanes can serve as a fascinating synthetic tool for the synthesis of different important organic compounds with various functional groups. So we can classify the reactions of haloalkanes into three main categories. The first one, nucleophilic substitution reaction. Second one, elimination reactions. And the third one, reaction with metals. Now we will study each one of these reactions step by step. Now we will discuss the first type of reaction of alkyl halides, that is nucleophilic substitution reactions. We know that the carbon-halogen bond in haloalkanes or alkyl halides are polar in nature. The halogens are more electronegative than carbon. So the electron density of carbon-halogen or CX bond in haloalkanes or alkyl halides is displaced towards more electronegative halogen atom, giving the halogen atom a partial negative charge, that is delta minus, and this carbon delta positive charge. Now this delta positive carbon is subjected to attack by electron-rich nucleophile. Now what is a nucleophile? Nucleophile means nucleus loving. Philia means love. So a nucleophile is a reagent that loves or seeks a positive center. So a nucleophile should either be a negatively charged ion, that is anion like OH minus, or a neutral species like ammonia having at least one lone pair. Here, a negatively charged nucleophile attacks the electrophilic center of alkyl halides to yield RNU. Now, this nucleophile attacks this electrophilic center and RX bond is broken. So, this is bond making and this one is bond breaking. So, here X is substituted by NU. X minus is the leaving nucleophile. In this example, we have taken a neutral nucleophile. So in this case, a positively charged product is formed. Now this nucleophile attacks this electrophilic carbon and this RX bond is broken. So this is bond making and this one is bond breaking. Here also X minus is the leaving nucleophile. So in both the cases, X of Rx is substituted by Nu. So the group substituted or displaced is a halide ion, which is also referred to as the leaving group. We have learned two types of nucleophilic substitution reactions. SN1, that is substitution nucleophilic unimolecular, and SN2, substitution nucleophilic bimolecular. Let's recap the concept of SN1 and SN2 reactions. SN1 is a two-step mechanism. The first step involves the formation of a carbocation, and in the second step, the carbocation is attacked by the incoming nucleophile. Whereas SN2 is a one-step mechanism. Here bond making and bond breaking takes place simultaneously. It is referred to have a concerted mechanism. SN1 is favored by sterically crowded substrate, preferably 3-degree alkyl halides, whereas SN2 is favored by less crowded substrate. 1-degree alkyl halide is the best candidate for SN2 reactions. SN1 is favored by polar solvents, whereas SN2 is favored by non-polar solvents. Weak nucleophiles favor SN1 reactions, whereas strong nucleophiles favor SN2 reactions. SN1 is unimolecular. In the rate equation, only the concentration of alkyl halide will be included. But in case of SN2, it is a bimolecular reaction, and in the rate equation, it will include both the concentration of alkyl halide as well as the concentration of the nucleophile or OH minus. In case of SN1, if the substrate is optically active, then racemization takes place. Whereas in case of SN2, inversion of configuration takes place as because there will be rear side or back side attack. Nucleophilic substitution changes the functional group in a molecule. So the nucleophilic substitution reaction of alkyl halides will help us to synthesize many important organic compounds of different functional group from alkyl halides. Let us see the transformation one by one. The first reaction is substitution of halogen by hydroxyl group or conversion of alkyl halide to alcohol. This alkyl halide Rx reacts with boiling aqueous KOH to yield alcohol ROH plus KX. This KOH dissociate to give K plus OH minus. This OH minus is the attacking nucleophile. Now this OH minus attacks this carbon of this R group and RX bond is broken, leading to the formation of ROH and X minus, that is halidine, is the leaving nucleophile. So here we have ethyl bromide. So ethyl bromide in the presence of boiling aqueous KOH, or it can be boiling aqueous NOH, it will give us ethyl alcohol plus KBr. So if you want to convert ethyl bromide to ethyl alcohol, we have to use aqueous KOH. Stress on the word aqueous. Similarly, we can also get alcohol ROH from alkyl halide. Here we have alkyl iodide. By reacting this alkyl iodide with moist silver oxide, which is represented as AgOH. So Ri plus AgOH will give you ROH plus silver iodide. So we can convert alkyl halide Rx to ROH either by using aqueous KOH or aqueous NaOH or moist Ag2O. Now we will study the second substitution reaction, that is substitution of halogen by cyano group or conversion of alkyl halide to alkyl cyanide. Alkyl halides react with alcoholic potassium cyanide solution to yield RCN, that is alkyl cyanide plus KX. Let us see how potassium cyanide reacts with methyl chloride. Now potassium cyanide dissociates to give K plus Cn minus. So here Cn minus is the attacking nucleophile. This Cn minus attacks this carbon and CCl bond of methyl chloride is broken, leading to the formation of methyl cyanide plus chloride ion. This is the leaving nucleophile. So potassium cyanide reacts with CH3Cl to give us CH3Cn. Similarly, we can substitute halogen by isocyanide group. So our third substitution reaction is substitution of halogen by isocyanide group or conversion of alkyl halide to alkyl isocyanide. Aqueous ethanolic solution of alkyl halides on heating with silver cyanide yields alkyl isocyanide plus Kx. This is ethyl bromide. So ethyl bromide reacts with silver cyanide to give ethyl isocyanide plus silver bromide. We have learned that alkyl halide with KCN give us RCN, that is alkyl cyanide, and the same alkyl halide with silver cyanide will give us alkyl isocyanide, that is RNC. This RCN alkyl cyanide and RNC alkyl isocyanide are isomers of each other. Now what is the reason behind this? We know that cyanide ion is an ambidentate nucleophile. Cyanide ion can attack the alkyl carbon of alkyl halide either through carbon end or through nitrogen end. If cyanide ion or cyanide nucleophile attacks the carbon atom of alkyl halide through carbon end, then RCN or alkyl cyanide will be formed. Now the cyanide ion, if it attacks the alkyl halide through nitrogen end, then alkyl isocyanide will be formed. Now KCN is predominantly ionic in nature, leading to K plus Cn minus. So in this case, cyanide ion attacks the carbon atom of alkyl halide through carbon end, leading to the formation of RCN, that is alkyl cyanide. Whereas silver cyanide is predominantly covalent in character. This is because Ag plus is having pseudo-inert gas configuration. According to Fagen's rule, cations having pseudo-inert gas configuration favors polarization, thus favors covalency. So AgCN is predominantly covalent in nature. So here attack occurs from the nitrogen end of cyanide and alkyl isocyanide is formed. Our next reaction is substitution of halogen by nitro group or conversion of alkyl halide to nitroalkane. Alkyl halide, when heated with ethanolic solution of silver nitride, reacts to form RNO2, that is nitroalkane plus silver halide. This is CH3CH2Br, that is ethyl bromide. This ethyl bromide reacts with silver nitride to yield nitroethane plus silver bromide. Now we will discuss substitution of halogen by nitrite group or conversion of alkyl halide to alkyl nitrides. Alkyl halide, when treated with aqueous solution of potassium or sodium nitrite, yields RNO2, that is alkyl nitrite plus Kx. Ethyl bromide, when treated with aqueous solution of potassium nitrite and heated, we will get ethyl nitrite plus potassium bromide. We know that alkyl halides, when reacts with silver nitrite, yields nitroalkane as a major product, whereas the same alkyl halide, when reacts with potassium nitrite, yields alkyl nitrite as a major product. This nitroalkane and alkyl nitrite are isomers of each other. Now, what is the reason behind this? NO2 minus is an ambidentate nucleophile. This NO2 minus can attack alkyl carbon of alkyl halide either through this oxygen end or through the nitrogen end. If the attack occurs from the oxygen end, then alkyl nitrite is formed, whereas if the attack occurs from the nitrogen end, then nitroalkane will be formed. Potassium nitrite is predominantly ionic in nature, leading to the formation of K plus ONO minus. So attack occurs from the oxygen end of NO2 minus. This is KNO2, O minus of NO2 minus attacks this R and RX bond is broken, leading to the formation of alkyl nitrite. Silver nitrite is predominantly covalent because Ag plus has pseudo-inert gas configuration. And according to Fagin's rule, cations having pseudo-inert gas configuration favors covalency. So in this case, attack occurs from the nitrogen end of NO2 minus, leading to the formation of nitroalkane. So today we have discussed nucleophilic substitution reactions involving conversion of alkyl halides to alcohol, alkyl cyanide, alkyl isocyanide, nitroalkane and alkyl nitrite. In our next class, we will discuss the conversion of alkyl halide to ether and amines. And we will also learn the preparation of higher alkynes from acetylene using alkyl halide. Thank you.